So here is an example of utilizing the conservation of rotational kinetic energy. A uniform rod PQ of length 2L and mass m, or is a rod of 2L mass m, Q is attached to a circular disc of radius L and mass m. The two objects are coplanar. The motion of the system as a whole initially starts horizontal but undergoes rotational motion until the system is perpendicular to the ground. Firstly, find the moment of inertia of the system about an axis through P perpendicular to the disc, so keyword perpendicular, and show that when the system rotates about this axis and hits the ground, omega is the square root of 48g over 65L per second. So this is a very difficult question, I'll admit, so if you want you can try it, but if not you can stay around for the solution. So this is the diagram of what's going on, and we start with finding our moments of inertia. So the moment of inertia about P is just the moment of inertia of a rod, which is 4/3 ml squared. And then the rotational, or moment of inertia for here is 1/2 ml squared. So if we let C be the axis through, or the center parallel to P first off, then we can use the parallel axis theorem, say that IP is IC plus MD squared. So we have IP is 1/2 ml squared plus m by 3l squared. So that's the distance from C to P. So that'd be 19 ml squared over 2. Now using the perpendicular axis theorem, we can add 4/3 ml squared, which is the moment of inertia of P, to the moment of inertia of D, or of this compound here, which gives us 65 over 6 ml squared. So now onto the actual problem. We have two positions that the object can be in. First, it's directly parallel to the ground, and after, it's perpendicular to the ground. So we firstly have the initial potential energy of the rod plus the initial potential energy of the disc plus 1/2 I omega squared of the rod and the disc. And then that must equal to the potential energy, the final potential energy of the rod plus the final potential energy of the disc plus the final rotational kinetic energy of the system. So it's initially at a height of 4L, both of them. We're talking about the centers of gravity here. So the center of gravity of the system is here. So both of them are of height 4L, and it starts from rest, so omega is 0. Then we have 3 mgl because the circle has a radius of L, and this is of length L, so the center of gravity of the rod is of a height 3L above the ground. In a similar way, the height of the center of gravity of the disc above the ground as it hits it is of length L. And then 1/2 I omega squared, but we already found I of the system, which is 65/6 ml squared times omega squared. So after simplifying things down, we get to 4 mgl equals 65 over 12 ml squared omega squared. Now cancelling the m on one of the l's, we get 4g is 65 over 12 l omega squared. So then multiplying by 12 divided by 65l and taking the square root, we get omega is 48g over 65l per second as required.